Welcome everyone to a new episode. Today I'm talking to Román Orús about variational quantum non-orthogonal optimization. This paper is about how you take optimization problems and particularly encode the optimization variables in qubits. I'm going to let Román introduce the details of this, and I hope you enjoy what he has to say. Román, thank you very much for taking the time to join today.
Yeah, hi.
We have the paper on the screen that we're going to be discussing. It's called Variational Quantum Non-Orthogonal Optimization. As a starting point for this discussion, would you mind just talking about what led to the publishing of this paper and why you chose to investigate this topic more closely?
Yeah, so let's see. So this paper is about quantum computing algorithms, okay, in particular for optimization. And the main motivation for this paper was that, well, as you know, we have quantum processors nowadays, okay? There are different types of quantum processors, but all of them, as of today, so they are limited in capabilities, okay? So, you know, the quantum processors that we have today, they have a limited number of qubits, they are noisy, okay? And this implies that you cannot run very long calculations on them. And also you cannot have, you cannot have too many qubits, so that it's difficult to actually solve problems that are real-life problems, let's say, that are relevant for industry with many variables and so on, okay? Because the processors are themselves limited by capabilities. Now, what this paper is trying to do is to understand what are the possibilities of these processors, okay? So from our perspective, these processors can be used for more things than what the people initially thought about, okay? Because of, by using some tricks of quantum mechanics, we have shown that actually it's possible to encode more variables to solve optimization problems than what was originally expected. And that's what we actually do with this paper. In this paper, we propose a new quantum algorithm, okay, that uses some interesting types of encoding of variables in the qubits of the system, but allows to actually solve much larger problems than what originally was expected with these small machines, okay? So in a way, this is actually making the actual and the current quantum computers, which are small, okay, this algorithm is trying to make them useful, okay, for practical applications.
Right. If we talk perhaps about the encoding of this to begin with, I want to get back to the optimization problem that you use for benchmarking later on with this polynomial optimization. But if we go to this figure, I think that could be an interesting starting point to base the discussion around. So from my perspective, the entire paper centers around the idea that we see here, namely that we have some encoding of classical discrete variables onto the block sphere in a particular way. Would you mind describing the intuition behind that a little bit more? What kind of assignment you would have for these classical values onto the qubit, and how that differs also historically from what's been done?
Yeah, exactly. So when you have an optimization problem with discrete variables and you formalize it in terms of bits, this is like the typical, combinatorial optimization problem in mathematics, okay? And there are many problems that fall into this category, like the satisfiability problem, the traveling salesman, and so on and so forth. Now, when you want to solve this, you see that the actual cost function is described in terms of bits. Okay, bits are variables. These are classical variables. Okay, they can take two values. Okay, they can be either 0 or 1. Now, when you want to solve this with a quantum computer, the first thing that comes to your mind is to say, okay, so then I have this classical cost function, right? And the way in which I'm going to encode this, the solution of this on a quantum resistor is by using one qubit for each one of the classical variables. Okay, now, this is a very good approach when you start, but at some point you realize that this is probably not the best thing that you can do. And the reason for this is that, a qubit is not a bit. Okay, a qubit is a quantum two-level system. Okay, it's essentially a Hilbert space of dimension 2, and there you have lots of states, okay, that you can access apart from 0 and 1. I mean, what this picture is representing here, for instance, is the Bloch sphere of a qubit. The Bloch sphere is the set of all the accessible states of one qubit, okay, of one isolated qubit to be more precise, and in this sphere you can access all the, not just the 0 and the 1, which are the poles of the sphere. These are the classical states, no, but you can also access all the rest of the states that are on the sphere, okay. That's for an isolated qubit. If you, on top of that, consider a qubit that is not isolated, you can even access the interior of the sphere. Okay, so this gives you many more states per qubit that you can access, okay, than just the classical configurations 0 and 1. So what we thought is that, well, instead of encoding one bit variable per qubit, since we can access many more states in the block sphere than just 0 and 1, then why not trying to label, okay, different states in this block sphere, okay, so that we can access a larger number of variables per qubit, okay, and that's exactly what we do. What we have in this representation here is actually, we have a polyhedra that is inscribed inside of the block sphere, and the vertices of this polyhedra are actually points, are actually states that we are labeling as different configurations, okay, of the optimization problem. Now, this is a bit tricky because all these states, they are not orthogonal among themselves, and this implies that they cannot be distinguished with 100% efficiency and accuracy just by doing quantum measurements, but they can be estimated using quantum tomography, okay? And this is this is our proposal in the paper, just to use more states than just 2 per qubit to codify the information of the classical cost function. Yeah.
Mm-hmm. Okay. If we look at the placement of the encodings here in the figure, is this placement that you would have agnostic to the kind of problem that you're trying to solve? I'm thinking about this from a practical point of view now, because I guess that the placement of these would be, in theory, context dependent, what you would like to have in terms of encoding.
Yeah, but this is agnostic because what you want with this encoding is that these states can be, let's say, distinguished in the best way that you can. Okay, now we know from theorems in quantum information theory that the states that can be more efficiently distinguished by doing measurements are those that are maximally orthogonal between themselves. Obviously, if you have 2 orthogonal states, you can distinguish them with just one measurement, okay? That's just distinguishing between the 0 and 1, for instance, or between plus and minus. But if you have 2 states that are not orthogonal, then you need more than one quantum measurement, okay? Now, we know that the ones that are optimal, in the sense of what is the minimal number of required measurements to distinguish these 2 states with a given accuracy, okay? These are the ones that are maximally, let's say, maximally orthogonal among themselves, okay? And these are the ones when you traduce that into what states are these states in a block sphere, this translates into the ones that correspond to the vertices of a polyhedra. So for instance, if you wanted 3 states that are maximally orthogonal for 1 qubit, okay, then you will have probably one state could be the 0, okay, and then you have 2 other that will be, making 120 degrees angle, okay, with the original vector, okay. If you have 4 states, you will have a tetrahedra, okay? If you had 5 states, you will have a polyhedra with 5 vertices, and so on. Yeah. And this is agnostic to the problem.
Yes,
okay? It's actually a requirement to distinguish the states as best as you can. Yeah.
Mm-hmm. Yes, I agree that the kind of encoding, or that the way you figure out what the maximally orthogonal states are, is agnostic to the problem. My question is more about, given that you've now placed these vertices on the block sphere, that you would like to encode your values, the placement of the actual values, at least as far as I'm able to tell, would have an implication on what the solution is for a given algorithm. Because these states are maximally orthogonal, but they're not completely orthogonal, right? Is there a way to think about how that placement should be appropriately done in a scenario where you want to apply this in some form of algorithm? Or is that something you're not treating in this paper? Or you're not treating in this paper, but like in general?
Yeah, that's a good point. So I agree that depending on the cost function and the actual problem, depending on whether there is a bias towards a particular configuration or not, there may be an optimal way of choosing these states within the block sphere. Okay, but we didn't discuss that. Okay, we think that's problem dependent, and in practice, what we did was to we just choose that one of the vertices is always the state 0, I think, and then from there we construct the rest of the states, and that in practice that seems to work pretty well.
Mm-hmm. Okay, understood. The second point that you mentioned that I want to get back to is when you said that you could encode parts inside of the block sphere as well. If you had, I think you said entangled qubits, or
yes.
Could you paint a bit more of the picture, like how that would work? What is that kind of application where you would require to have multiple qubits to encode one state?
Yeah, exactly. So here the encoding that we are doing in this picture is only on the surface of the block sphere. Okay, so these are the surface of the block sphere is encoding the pure states of a qubit. So we are encoding, states, okay, that correspond to a qubit, that is in a separable state with respect to all the other qubits. All right. We could have done a more tricky encoding, and we could have chosen also points inside of the blogosphere. That could also have been possible, okay, because the states inside of the blogosphere, they are also accessible states to the qubit, okay, but this means that the qubit is entangled with the rest of the qubits. When one qubit is entangled with the rest of the system, when you compute the reduced density matrix of that qubit, okay, you realize that it's actually a mixed state because it's entangled with the rest. And when you represent this mixed state in the blogosphere, it gives you a state on the interior, okay. Well, we could have also chosen states on the interior of the sphere. Why not? This will correspond to a quantum computation where you run the quantum circuit, okay, and at the end of the computation, when you do the measurement, instead of having a separable states of all the qubits, you have an entangled state of all the qubits, okay? And then, you estimate points inside of the blogosphere of every qubit. This could have given us, more power in terms of representability. We could have access many more states per qubit, okay? Many more classical configurations, let's say, per qubit. However, it's also, more fragile because at the end of the day, we are saying that you have to stop the computation at a point where the quantum state of the quantum resistor is actually highly entangled, for instance. And this is something that is very sensitive to errors and to noise and so on. So this is why we prefer not to do it. But in principle and a priori, and mathematically, there is nothing against that. I mean, this is something that we didn't implement it explicitly in the paper, but we could have done it, okay, if necessary as well. Actually, we discussed this also on a follow-up paper that we did after this one, where we generalized this idea to actually continuous encodings on the blogosphere, okay? And there we had some example where we actually ran some simulations for points on the interior, and it was actually working. It was harder to estimate, okay, also numerically, but it was working as well. Yeah.
Okay, what's the idea then? So let's transition to the continuous case because you had a paper on that. If you would encode that internally in the block sphere as well, would you have like an interior shell that you also use, or would you leverage, for example, like the entire dimension? How would that work in terms of?
We can leverage the entire dimension. So you can codify the entire block sphere with two angles and the radius, okay. And the idea here is that if you only use the two angles, you can encode two continuous variables, okay, which correspond to the surface of the sphere. But if you consider also the radius, then you have a third continuous variable that you can encode on the sphere. Yeah.
Okay. If we consider potential problems where encoding the interior of the sphere would actually be necessary, do you know of any such problems, let's say, beyond the scope of physical simulation? So I guess with physical simulation, you could have plenty of instances where the results should be some form of entanglement between the different qubits. Are there any other applications where that kind of encoding is strictly necessary that you're aware of?
No, I think it's an option. Okay, so at the end of the day, this is we are going to be using this to solve optimization problems, and you choose the type of algorithm that you want to use. Okay, if you want to use an algorithm that encodes, let's say 1 bit per qubit, then you have the traditional encoding. If you want to choose an algorithm that encodes more than 1 bit per qubit, but just working with pure states, then you are encoding things on the surface of the sphere, and that's fine. Now, if you want to do quantum circuits that probably have more entanglement capabilities, and perhaps you want to avoid local minima, or you have more complex optimization problems, maybe then it will be useful to choose encodings that allow also for the interior of the sphere, perhaps, and then the quantum circuit probably has to be shorter as well, okay? Because you stop the computation at a point where everything is still entangled, but maybe that's already sufficient, no? So I don't know. I think that depends really on the problem. It's just different alternatives that we have there. I don't think there is really a problem for which this is necessary 100%, but to me this is just we have a menu of algorithms, okay, and well, we can just try with one or with the other, okay.
Okay, good. So let's focus on the optimization problem that you use for benchmarking of this. So we're talking specifically in this paper about polynomial optimization. Could you describe what the general procedure is for optimizing a polynomial up to this point?
Yeah, exactly. So we chose polynomial optimization because this was a very clear example of how this will work. Okay, so if you have a polynomial, okay, of different variables, the traditional way in which you will have been solving this on a quantum computer. So imagine that you want to solve this on a different type of quantum computer that is not based on a quantum circuit. Let's say, imagine that you want to do it with quantum annealing, for instance. Then you will say, okay, I'm gonna, well, I have my polynomial, okay, and then I have my continuous variables, then I'm gonna discretize these continuous variables in terms of bits, okay? And then you choose a bit, a depth for each one of the variables. Let's say you represent each continuous variable in terms of, I don't know, 10 or 20 bits, okay, depending on the accuracy that you want. And you have this for each one of the variables, okay? Now, at some point you realize that the target function that you have depends on many bits variables, okay? And since it's a polynomial and it involves products between the original variables and powers and so on, then it's a high degree polynomial, okay, of bit variables, okay? It's actually what we call a higher order unconstrained binary optimization problem. It's higher order because, you know, it's the order of the polynomial can be very high, okay? You have lots of variables multiplied with each other. And it's binary because the variables are binary. And this is one of the hardest problems that you can find in combinatorial optimization to solve, okay? I mean, just to give you the feeling, you know, traveling salesman, satisfiability, and all these problems are quadratic, okay? So these correspond to polynomials of degree 2. So once you start putting polynomials of much higher degree, you can also reduce them to a quadratic problem at the expense of having to add a lot of redundancy and so on. So this is very costly, okay? Now, obviously, if you want to solve these problems with a quantum computer, you need many variables, okay? You have a problem with many variables, and solving this with the traditional encoding is most of the time simply impossible, okay? Now, what we saw is that with our encoding, it was actually possible to handle all these variables and solve the polynomial optimization efficiently. Yeah.
Okay, I understand. So if we're talking about the stability of these kind of applications to the optimization problem, specifically for polynomials, is this a approach that's generally taken now? Like, let's say you wanted to use quantum computing particularly for the optimization problem of polynomials. You could use adiabatic quantum computers, or you could use something gate-based like we're approaching here. As of right now, taking, let's say, the current status quo, which doesn't involve this kind of encoding, what is the preferred way of solving those problems right now? Is that adiabatically, or would you use?
Yeah, I will say that until now, the preferred way was using adiabatic quantum computing, but simply because the hardware was more evolved. Okay, we have more qubits available on an adiabatic quantum computer, on a quantum annealer, than the qubits that are available, let's say, on a gate-based quantum computer. Okay, and that's the reason why I think that until recently the preferred solution was tending to be quantum annealing. Okay, I think this tendency is changing because of two reasons. The first one is that gate-based quantum computers, they are becoming more and more powerful. Okay, that's true. We have an increasingly larger number of qubits every year for quantum processors. Okay, you know, the big companies, IBM, Google, and so on, they have these roadmaps that they are fulfilling, and this is very impressive, no? So this is thing number one. And thing number two is that also the community are thinking very hard about algorithms to solve these problems on these machines. And that's exactly, this paper is one example of this, okay? Thanks to these types of developments, so thanks to results such as the ones that we presented in this paper, it's actually possible to use machines that a priori you will say, well, this is too small to solve anything useful. Well, no. Actually, we have to reconsider that because now we have an algorithm with a different type of encoding and a different type of, handling with the information that shows you that you can actually embed a very large problem in this type of quantum computers. And this, in combination with the fact that the hardware is also improving, okay, every year, I think that the tendency is nowadays more and more to go towards gate-based quantum computers. That's my feeling, okay? Which are also universal and so on. So that makes perfect sense. So I from my point of view, I think now we are transitioning from a period where people were very happy of using quantum annealers to a period where I think the people are going to be using more and more, let's say, gate-based quantum computers.
If we think about the kind of algorithms that a gate-based quantum computer would use to solve a problem that you've now encoded in this way, we have QAOA, and I think also VQE is what you're mentioning in the paper. If we think about those approaches, how would they be modified if you have this kind of encoding now in the block sphere?
Yes, so let's see. There are QAOA and VQE. They are very similar in spirit. Okay, they are both variation algorithms. The only difference is is the type of variational quantum circuit that you use. In QAOA, it's adapted to the actual structure of the problem. In VQE, it's kind of more an ansatz that you just choose to work with. No? The way in which you have to modify these algorithms to apply what we say in this paper is essentially at the last step. So there is this optimization, classical optimization loop. Okay, this works exactly in the same way. The only difference is how you estimate the classical cost function. With the traditional encoding, you just make the measurement of the qubits and compute the cost function. Okay, with our encoding, actually, what you have to do is tomography. Okay, of each one of the individual qubits. Right? Tomography means exactly you have to guess by doing some quantum measurements what is the quantum state of each qubit, because now it's not just 0 or 1, it could be some other quantum state in the Bloch sphere. Okay? So this tomography step is what you have to add, okay, at the last step when you do the measurements, okay, on the qubits. Instead of just measuring on the basis 0 or 1, what we are saying is that you have to replace that with quantum tomography of the individual qubits. Okay? And with that, once you have estimated that, you can read the value of the cost function and repeat the optimization loop. Okay, that works exactly in the same way. Yeah. Now, this optimization step, it may be costly. Okay, optimization. This tomography step, it may be costly. Okay, it's something that it's actually when you have to do many quantum measurements, something that it's even an open problem nowadays in quantum information science. But it's true that for when you don't go to too many states on a Bloch sphere, it's something that is it can be realized, okay, without too much overhead. At some point, you have to think about a trade-off here, okay? What is easier for me to do? To get more qubits and do the traditional encoding, which may be technically complicated, or to just do more quantum measurements and use this number of qubits, okay? So sometimes when it comes to having something practical, it may be faster to actually do more measurements and implement the quantum tomography than just try to implement the technology, okay? So at some point you have to play with this trade-off.
When you say that you would have to do more measurements, are you talking about really individual measurement sequences? Because the reason why I'm asking that question is whether or not this cost that we're talking about now bleeds over in terms of fidelity in the system. Like, is it that your fidelity is not affected by this cost, or is the fidelity itself also decreased by it? Do you see where I'm coming from with the question?
No. So you need a number of measurements for each one of the individual qubits. But this is a single qubit problem. If you have a qubit with an arbitrary state on the Bloch sphere, okay, or maybe or when you don't know what is the quantum state of the qubit, so there are theorems that there are optimal, let's say, measurement sets. Okay, these are called POVMs in quantum information that tell you with a large, let's say, probability what is the most probable state of the qubit. Okay, so this has been studied for one qubit and so on, and depending on how many measurements you can do. I mean, there are people were doing a lot of this research back in the early 2000s, actually. So this is something that is well characterized, and these are the measurements that I'm referring to. Okay, these are the ones that we have to do. Now, it's also true that in practice, one may have to be careful because since these are not, let's say, projective measurements, that they are just measuring on 0 and 1, let's say orthogonal, one has to be careful that, the rest of the system, when you implement all these strange measurements, the rest of the system also has to be well behaved, you don't introduce too much noise, and so on. But well, that's again something that people have been working about that also for years. Okay.
Yeah. Okay. If we transition to the cost function that's associated with the particular benchmarking problem that you have, it's illustrated here. And I think there were a couple of remarks regarding the smoothness of this and also how that compares to some of the previous approaches that have been done before. Could you maybe say a few words as to why the cost function is not very smooth in this case and what potentially underlies that and how we might be able to get around that problem in the future?
That's actually a good point. The optimization problem is full of local minima, okay, and also barren plateaus, and it means that it's what we are targeting here at the end of the day. Obviously, we would like to have the global optimum, okay, but in practice, most probable outcome is that we will end up finding a local minima, okay. Now, the point of this optimization is that obviously since the states that we have, they are not orthogonal, okay, then they are very sensitive to the actual value of the cost function. And then this is the reason why we see all these oscillations, right? what we saw is that the more, and this is a bit counterintuitive, what we saw is that the more states we included in the blogosphere, the smoother was the evolution, okay? Because the distance between two different values of the variable was actually very small, and then it was very easy for the system to transition between the two. There were not very big jumps on the blogosphere, okay? So I think we made a comment about this on the paper, that actually when we increased the number of states accessible per qubit and went to the limit of the continuous variable, actually this becomes smooth, completely smooth, okay, this optimization. But yeah, I mean, looking at these jumps, okay, this is exactly the fact that, you know, we have here an heuristic algorithm for which we have to optimize it heuristically with, let's say, gradient descent, because it is variational, and therefore we see these jumps going up and down. I mean, the important thing here is that obviously we need to repeat this many times, and at the end of the day, reach something that keeps going down, okay? And that's exactly what we saw.
Mm-hmm. I guess that brings us back a little bit to the way, or to the point we discussed in the beginning of how you place the encoded states on this block sphere. My understanding now with what you were saying is that you said as we go in the limit of, you know, adding more and more states to this, it becomes smooth. That tells me that in these vertices that we're now placing our variables that we're encoding, that we would start with, let's say, 0 here somewhere, and then 19 would be on the exact opposite side of the block sphere, and then you would sort of encode it in a more or less a spiral, I guess, to maintain that the vertices that are close to the one you're considering now are always close also in value, so that you don't have sharp gradient somewhere along this block sphere. Is that correct?
Exactly, yeah. That's exactly the point. Yeah.
Okay. Good. The last thing I want to check with you has to do with this particular schematic here for the circuit diagram that you implemented. When we're talking about these, and I take it that this one is particularly for the optimization of this kind of polynomial. Yeah. If we're talking about these in general, when we're optimizing for polynomials, do we need to always update the entire circuit diagram as a consequence of changing some parameter of the optimization, or how robust are these against changes?
Oh, that's a good point. I mean, in practice, what we do is to implement this. Obviously, the quantum circuit is an answer that you choose. Okay, we chose this circuit because it was easy to implement, but we have been choosing some other type of quantum circuit that added more entanglement, okay, in the system and was more complicated. No. When it comes to the actual optimization, in this feedback loop that we have, okay, with gradient descent, at every step we have to optimize all the parameters in the circuit, okay, all of them. That's the optimal thing to do, okay. Now, having said this, it's true that there may be more efficient strategies by optimizing the parameters, let's say one by one, okay. This is something, for instance, and then this is less sensitive to actually big variations of the cost function and so on. This is actually something that we use in other variational optimization algorithms. Okay, for instance, when it has nothing to do with this paper, but in classical, for quantum many-body systems, there are all these family of algorithms that are based on tensor networks. Okay, for which the optimal optimization strategy there is actually to go, parameter by parameter. Okay, this is something that we could have done also here. Okay, and we didn't implement it. Actually, we also didn't discuss it. But I may assume that may actually make the algorithm more robust to errors, okay, or to variations of the cost function as well. Yeah.
Mm-hmm. Okay, a bit of an excursion here from the paper itself. If we're comparing different architectures and how you would go ahead with solving these kinds of optimization problems, specifically for polynomials now, is there a significant difference in the complexity of constructing the quantum circuit if we compare something like adiabatic to gate-based quantum computers?
Yeah, well, it depends. This is only for gate-based quantum computers, and then for gate-based quantum computers, it's true that depending on the type of underlying quantum hardware, it's easier to do one type of circuit or another. Okay, I will say that, for instance, if we are using superconducting qubits or quantum dots or any type of artificial qubit, then all the topology of interactions is based on an artificial lattice of interactions that you have to do. And therefore, the closer the quantum gates are to the actual topology of the lattice, then the easier it is to implement. No? This makes it difficult to make, for instance, long-range 2-qubit gates. Okay. So imagine that. I mean, it's not the case of this quantum circuit, but perhaps if we had a very large quantum circuit with gates to entangling gates between all the qubits, then I will imagine that that would be easier to implement in another type of hardware that involves all-to-all connectivity. Okay, and for instance, neutral atoms, okay, or Rydberg atoms, or ion traps. Okay, also, which allow for long-range interactions between the different qubits that would have been easier. Yeah. So I don't know. I mean, as of today, the processors that are more developed are the ones based on superconducting qubits and maybe also neutral atoms. But I will say that if one needs to add more entanglement into the system for very complicated optimization problems, then maybe, but this is just a guess. Okay, this is just a guess. Maybe an architecture that allows for all-to-all connectivity will be more appropriate. But I may be wrong. I don't know. Okay.
Okay. Thanks. The last thing I want to ask you about is future research as a consequence of the things that you've now presented. Given that we have these promising findings, I would say, for this kind of encoding, what is the next thing that you would like to try out along this road? Are you testing some other approaches as well that are sort of closely related to this, or is there anything else you would like to say in terms of next steps for your research?
Yeah, obviously the first thing is to implement encodings also with the interior of the sphere. This we didn't do. And also to improve the quantum tomography protocols for measuring the states of the qubits at the Bloch sphere. Okay, this is something that has to be done. Another thing that we are exploring right now is the generalization to continuous variables, as I was saying, and how this applies to practical problems in optimization. Because once you can optimize continuous variables, you can do many things in practice. Okay, you can actually do Fourier analysis. You can do and once you can do Fourier analysis, you can do other types of transforms. You can solve partial differential equations and so on. This is something that we're exploring now. And coming back to the actual discrete cases we have here, yes, obviously now our goal is to try to use this and ideas related to this to actually solve large problems that are relevant for, let's say, for industry or for academia and so on. I mean, not just toy problems with a very small number of variables, but we are trying to attack a large number of variables already with superconducting qubits, for instance, and so on. So this is something that we are trying to do right now, okay? And we'll see how it goes.
Mm-hmm. Okay, wonderful. Last question I have is, for the wider research community that are interested in this as well, is there anything else that you would advocate for them to investigate, like some parts of the research that you would like to see get more attention that are different from the ones that you're personally, let's say, looking to dive deeper into?
Yeah, I would like to see the people exploring more possible and exotic encodings, okay, of classical cost functions into a quantum system, okay? Because obviously there are many other ways of encoding things on a quantum computer. These are not the unique ones that we could explore, but I think that there may be exotic ways of encoding information, okay, that will probably allow for quantum processors to boom even faster, okay? As I was saying, we are trying to understand for what these quantum processors are actually useful, the ones that we have nowadays, that they are small, noisy, and so on. And obviously we can improve this in two directions. We can improve the hardware, but this is a work of the hardware guys. So the better hardware, the better for everybody, okay? But it's also a task for the people doing quantum software, okay? We have to invent new algorithms and new original ways of encoding information on a quantum computer that allows us to actually use these limited machines for things that are useful. This is not easy because we are so used to think in terms of classical computers that we are somehow kind of stuck, okay, in that sense. And suddenly we realize that, hey, no, we have these quantum computers, we can encode information in many more degrees of freedom than we have, and we can actually use that. So I would like to see the community actually thinking more in this direction, and also how to implement other types of things on these algorithms, say, for instance, symmetries and things like this. This will enhance a lot the performance, okay, and make the algorithms, make these machines much more useful than what they are today. Yeah.
Mm-hmm. Perfect. So with that, then I think we can close the interview. Roman, thanks a lot for taking the time to join.